Hi, my name is Jia Hongwei. I'm now a fourth-year PhD candidate from UC Santa Cruz. Today, it's my great pleasure to share our recent work, To Aggregate or Not, Learning with Separate Noisy Labels. This is a joint work with Zhaowei Zhu and Professor Yang Liu from UC Santa Cruz, Tian Yilo from Amazon Search Science and AI, Ethan Ahmed and Abhishek Kumar from Google Research Brain Team. This work is primarily considering about learning with multiple cross-source labels where for each training images or training test data set, we have K annotators. Whether should we aggregate these multiple labels into one single label or not? So this is the basic question we are interested in. And now let me walk through some preliminary knowledge to help you understand our work. So basically, we are interested in the noise labels or the cross-source labels. If we denote by X as a feature, Y as a clean label, tilde Y as a noise label. Here are some example several 100 images given here. And several 100 data set is just a image classification task where each image belongs to one of the 100 classes. So under each image, we have two lines of text. The first row indicates the ground truth labels of this data set. And the second row indicates the human annotations we obtained from Amazon Mechanical Turk. So as you can see here that the human annotations might be mismatching with ground truth labels. So we can view this kind of mismatching or the cross-source labels as noisy labels, which is captured by the tilde Y, these notations here. So how do we characterize this kind of flipping? That is flipping from clean labels to the cross-source noisy labels. In this work, we try to adopt two kinds of transition models. The first one is the instance-dependent noise transition matrix, where the element of the transition matrix S row, this column indicates that for this instance X, the conditional probability that the clean label is Y, the clean label is I, by being flipped into the noise label J. So in this case, you can see that some feature X may appear only once in real-world data set. So it's super hard for theoretical analysis because we can't get so many transition matrices for the training data set. So for the assay of the theoretical presentations, we'll adopt a simplified version where we assume that each instance shares the same transition matrix T, which is TIG here. For example, suppose we have 100 dog images, but 20 of them are wrongly annotated as a cat. Then we will have the dog's row and the cat's column of the transition matrix will be 20 over 100. That is 0.2. So this is a brief examples about this class-dependent noise transition matrix that we are interested in. So our task is learning with separate noise labels. For example, considering a M-class classification task, the instance X as label Y are drawn from the joint data distribution D. In the clean label scenario, the learner will have access to maybe capital N training data points like SN, YN here. But in practice, our task is interested in the setting where we don't have this ground truth label YN, but instead for each instance XN, we will have a set of noisy labels or the cross-source labels to the YN here. This notation here means the I indicates the sample index here. And I indicates the annotator ID. And later we shall introduce the popular two learning paradigm in this kind of setting. So the first one is the label separation. Suppose in a binary classification task, remembering the noisy transition matrix we defined before, we can just assume it's of diagonal values as row 0 and row 1 here. So for label separation, what they do is just calculating the loss of each instance by referring to each annotations or each cross-source labels and get average for each instance as defined here. And the other learning paradigm is label aggregation, where they try to generate a single label via some label aggregation methods like majority voting or EM inference, so that the K noisy ones will be mapped into a single one, which we denoted as tilde YN, this solid circle here. And we assume that this aggregated noise label are generated according to some random variable tilde YN, tilde Y solid circle, and also following some transition matrix T here. So as we all know that the label aggregation can reduce the noise rate in the dataset. The noise rate means the amount of wrong labels in the whole training dataset. Here, the brief simulation of some existing denoising effect of label aggregation methods like majority vote, MV, or EM inference, EM. So in these figures, the x-axis indicates the number of labelers, and the y-axis indicates the number of noise rates among the dataset. For example, 20 means there are around 20% wrong labels in this training dataset. So the leftmost point indicates the ground truth, the noise rate by referring to ground truth labels when there is no treatment on these separate noise labels. As you can see that with the increasing of number of labelers, this kind of data quality is increasing, which means the amount of wrong labels are decreasing. So that's why denoising, that's why label aggregation method is very popular in literature, because it can indeed reduce an amount of wrong labels during the training dataset. So here, brief comparison between label separation versus label aggregation. So for some easy photos, you can see the left three photos, they're actually very certain human annotations, which means the majority of these workers would have a consensus on the class of this image. For example, the deer, the hen, or the house maybe. And in these settings, label separation and label aggregation have no differences on this kind of samples because they all agree on one specific class. But actually, for some uncertain human annotations, you can see the right three photos. These are the differences between these two treatments. For label aggregation, this will just force this kind of images to fit on one single label. But for label separation, it will form the soft human approximation for the classification tasks, because for some image classification tasks, it can be easy or hard for humans. So intuitively, some of the figures should contain some soft approximations or soft labels instead of one hard label. So in this case, we can see that label separation and label aggregation has different preferences. And our main task in this paper is try to address the concern that when we have a loss function L, how should we choose between label aggregation methods and the label separation methods? And moreover, when we have some, in literature or label noise learning, we actually have pretty many robust loss functions. And our another concern is that, what if we have some robust treatments on this kind of loss function L? How should we answer this question? Or how should we decide the preference between label separation or label aggregations? And our short answer is that label separations can be more beneficial when the label noise rate is large or the number of labelers is insufficient. This makes sense because when the number of labelers is very small or the dataset is of very bad quality, like very large noise rate, the denoising effect of label aggregation can be very bad. And moreover, it forces the deep neural nets to focus on a single label for each training image or training data, so that this can lose pretty much information instead of the soft information given by the label separation method. So we next provide a theoretical template to analyze the preferences between label separation and label aggregation. Our first step is try to analyze the model prediction bias. Suppose we have a pre-trained classifier f hat, which we define the bias of this classifier by referring to the optimal achievable base optimal classifier f star by this performance gap here. The first risk is actually the expected loss of this pre-trained classifier f hat under the clean label data distributions. And second one evaluates the performance of f star, which is the best achievable classifier f star under some hypothetic space. So intuitively, we are in practice by learning from the noisy label distributions, so that we would like to introduce some noise terms in these bias quantities. So we try to include one items and then remove one item. So we add these two terms here. And so that the bias can be decomposed into two parts. The first one is the distribution shift, which is actually quantifying the performance of the same classifier, but under different data distributions. One is the clean data distributions, and the other one is the noisy data distributions. And the second term quantifies the estimation error, where the prediction classifier is obtained through some noise label data distributions, but the ultimate classifier is obtained through some clean data distributions. So we will name this difference or performance gap as estimation errors here. So intuitively, this is a very nice decomposition of the Bayes term, but unfortunately, this is intractable because for this classifier, it's super hard to give some quantitative analysis on this one. So our solution is try to provide worst case upper bound of this Bayes term as a proxy for the analysis, which we bound these two terms with two upper bounds here. And we define this Bayes proxy as delta R, which try to capture the label separation when we replace U by this symbol, and where label aggregation will replace U by this symbol here. So we will try to compare the Bayes proxy of these two solutions. So our conclusion is that if we want to choose label separation method, we would like the separation Bayes proxy to be smaller than that of the aggregation ones. And by solving the previous proxies, we actually can get some constraints given in this equation too. So there are two key items here. We shall discuss about this constraint later. So these two terms are actually related to the number of labelers K. And we take the generic loss function L for examples. We give the closed form of alpha K and eta K here, and also gamma. So gamma actually, if we fix some probability measure, we can actually, and also number of training samples, this actually is a fixed term. So we are mainly interested in the left-hand side. The left-hand side, we have two key items. The first one is alpha K. Intuitively, this one captures the noise level between label separation and label aggregation. Label separation has no treatment on the denoising effect, so it will follow the original noise rate, but label aggregation can reduce noise rate. So alpha K try to capture the reweighted noise rate of these two methods, and it will calculate the noise rate gap. Intuitively, if alpha K is larger, it is because the label aggregation has a better denoising effect. So its label aggregation is much better, the alpha K would be very large, which makes this condition less likely to be satisfied. Another term is eta K here. Eta K is for the label separation method. This is because label separation method can introduce some richness factors. For example, we have the soft label informations. So instead of a one hot label, we have soft labels and we have more informations. So it introduces some richness of the data set. So in this case, the label separation will introduce a richness factor, which is larger than 1. And this term will all in all help make the constraint more easy to be satisfied. So you may want to ask that for this Bayes process, you are providing a worst case upper bound, but how tight is it? Actually, we show that our lower bound and upper bound almost follow the same orders. So this is very tight Bayes proxies. And that's why we try to use this Bayes proxy for the metric to help us decide whether we should choose label separation or not. And when we have some, I think there are some questions here. Okay, I will try to hurry up. So when we have some robot treatments, we can also, like loss correction or peer loss, we can also get the similar conclusions, but due to time limits, I won't go through details here, but actually the conclusions are almost the same as a basic generic loss function L. So they also take the same forms, so we don't go through details here. And for the peer loss function, we also have some related formulations. And to conclude, all these kind of conditions, like equations 3, 4, and 5, they also share the same template. The right-hand side is a fixed item, and the left-hand side has two items. One is because of the benefits of label aggregation, and second one is because of benefits of label separation. So we give some theoretical empirical simulations and conclude that actually when a number of labelers is small and the noise rate is large, this term will be much larger, and this term will be much smaller, which makes this condition very easy to be satisfied, which means label separation should be better than label aggregation in this setting. And we also have some theoretical empirical results to illustrate. We take 710 for examples, where it has around 50K training images and 10K test images, which each image belongs to one of the 10 classes. And we have two kinds of cross-out label settings. One is synthetic ones. We use some transitometry to simulate the cross-out labels. And the other one is the real-world settings, where we have two cross-out label data sets. One have very insufficient number of labelers, which is 3. The other one, it has sufficient number of labelers, which is 47. And this is overview of these results. You can see that in each subplot, we try to show the test accuracy of label aggregation and label separation under different number labelers, where the x-axis indicates the square root of number labelers. You can see that label aggregation is better. Here, label aggregation is actually by reporting the better results between majority vote and another method, EM inferences. You can see that when number labeler is small or the noise rate is large, the label aggregation is worse than label separation, and vice versa. And we also have some empirical results on real-world noisy data set. And you can see that Cypher10N, which has insufficient number labelers and relatively large noise rate, we show that separation is better. And for Cypher10H, we have sufficient number labelers, and also high quality of data, which is a very small noise rate. You can see that majority vote, the label aggregation is much better. So thank you for listening, and this is my overall work about this, my overall summary of this work. So if you have any concerns or questions, feel free to ask. And if we don't have time, you can also reach out to me through email or some other tools. Yeah, thank you for listening.